Hello everyone. My name is Jonathan Rose. I am a planning engineer at ERCOT in Texas. Hope you're doing well. Today I would like to share the ERCOT perspective of some model challenges with inverter-based resources and talk about a couple of case examples with inverter-based resources connected near series capacitors. I will start out the presentation by reviewing some ERCOT model requirements and talk about some of the procedures we have in place to ensure model quality, and then wrap up with some case studies near series capacitors. So ERCOT is very heavily dependent on good quality dynamic models, as I'm sure most areas and regions are. We have a pretty high penetration of renewable resources, a lot of wind, and a growing penetration of solar and batteries. We require three types of models: PSSE for general planning stability analysis, TSAT for operation stability analysis, and PSCAD for specialized EMTP studies such as subsynchronous resonance. To ensure model quality, all models must undergo testing, and this is to ensure quality and good performance. The owners are responsible for testing and providing the test reports, and I'll talk a bit more about that on slide 7. And of course, models must have appropriate documentation. So one of the focus on the panel is about black box models. So from ERCOT's perspective, black box models are not inherently problematic. We just need to be sure we have certain visibility and understanding of the model. For running, we need to be able to understand trip codes and error codes, be able to change the real and reactive dispatch, adjust voltage set point, and any tunable parameters. And for SSR studies, it's particularly useful to be able to disable protection or the SSR damping controls. Above all, we need to ensure that the models are correct, and that's why we have a lot of model requirements to help ensure confidence, including the hardware benchmarking requirement. I wanted to make a quick mention about user-defined models versus generic WEC models. So I know a lot of areas are requiring generic WCC models, but at ERCOT we do not require generic models. We do permit UDM models, and our standpoint is we just want accurate models. And whether it's a UDM or generic, as long as it meets our requirements, then we accept it. We've largely overcome any challenges with modeling many UDMs in the same simulation. In fact, our stability studies typically have over 100 renewable UDM models in them, and they run just fine. Computers are perfectly capable of simulating that. The reason we don't require generic models is because generic models often are always a simplification. It's to expect a single REG CAU model to represent all IBR devices. There's always going to be trade-offs, and there's always going to be a lag between the technology developed by the manufacturers and where the generic models are. And generic models have evolved quite rapidly, so that is sometimes a concern. We have seen several instances where UDM models lead to increased simulation accuracy. This is especially in areas of weak grid, low short circuit ratio. Certain details like the current rating and MVA rating of inverters as dependent on terminal voltage, that's very manufacturer specific, and the generic models really don't have a good way to capture that. So we have seen situations where generic models overstate the reactive capability when the terminal voltage is high. And another example in 2015, we identified a new interconnection project that was exhibiting momentary cessation, and we required it to be corrected before the project came online. And the only reason this was possible was because we had an accurate UDM model. I don't think at that time the generic models were even capable of representing momentary cessation. So that's one example of having a UDM model and provided a very useful accuracy increase. To ensure model quality, ERCOT has several requirements. These are listed here, and they basically all work together to help ensure model quality. The first is the hardware benchmark, and this isn't an in-the-field benchmark. We see that would be very difficult to do, especially for large signal disturbances like low voltage ride-through, high voltage ride-through. Instead, this is an in-the-laboratory benchmark, where usually an OEM would benchmark their inverter or turbine against some standard disturbances and compare it with the PSCAD model response. It's designed to verify correct model structure. It doesn't need to be site-specific. It can use generic settings. And it doesn't even need to use the entire inverter hardware. Some of the more bulky equipment could be represented virtually. It's really there to ensure correct model structure and provide a reasonable method to provide certainty there. To ensure we have the correct site-specific settings, we have a parameter verification requirement where once a project comes online, they must verify that the settings in the field, the tunable settings in the field, match the model, and they must submit evidence of that matching, such as screenshots or attestations. And then we have the model quality tests. These are simulation tests of standard disturbances that are run on the PSSE model and the PSCAD model. And this is to ensure good model performance, and it also provides a means to compare the PSSE model and the PSCAD model to ensure they're consistent. For any given plant, those two models should be consistent as far as the software is capable. So all these requirements work together. A lot of them apply before a project comes online, and then the parameter verification after it comes online. I'll talk about the PSCAD usability report in the next couple of slides. But more details about the model quality test can be found in reference number 2 here at the bottom in our DWG procedure manual. So some challenges we've encountered specific to PSCAD models. One is confidentiality is sometimes an issue. For example, running an SSR study, sometimes we see an issue that is only visible when the nearby plants are modeled. And in some of these areas with high renewable penetration, you can have a lot of nearby plants of different owners and different manufacturers. Maybe some Vestas, Siemens Gamesa, GE, so forth. And so we really can't share those models with developers or OEMs, and that presents a potential issue, because if we see, for example, subsynchronous resonance, then the OEM is really the only one that can adjust the controls to damp that out. And so the workaround we've used for that is an iterative process where basically we only send the plots to the developer, who then passes on to the OEM. And based on the plots, they make whatever adjustments to their model settings and send us back an updated model for testing. So it's kind of awkward in the iterative process, but it has worked. Another challenge with PSCAD models is model efficiency is a pretty big challenge. I mentioned we have some areas with a lot of high renewable penetration in a lot of projects, and so some of our simulations can have an upwards of 20 PSCAD site models in the same simulation. And PSCAD models are very detailed, so if you worked on them, you probably know that they're very computationally intensive and they can take a long time to run. Even on our very fast, high-performance, multi-core parallel processing computers. So it's not uncommon to see a single contingency take several hours to run. We've had some issues where they take an inordinate amount of time, 6 hours, and that really is because we have a couple of models that aren't really up to performance. When you have a model, for instance, one that requires a very small time step, then that will slow down the entire simulation. And so to address that, we've developed something we call the PSCAD usability guideline, or a PSCAD check sheet for short. And this is basically just a form that resource owners fill out to attest that the PSCAD model meets certain usability and efficiency features, such as various simulation step sizes and not requiring a very small time step, fast initialization, explain trip codes, etc. So this is a very useful check sheet. We expect the simulation issue to get better as more models are meeting all of the requirements on the check sheet. And the check sheet serves as a good vehicle to explain to OEMs what we want to see in PSCAD models. So if you're interested in checking out that check sheet, it is in the Model Quality Guide package, which is downloadable from this link. Okay, now we'll shift gears and talk a little bit about some case study issues, specifically challenges modeling IBRs near series capacitors. So you probably heard that ERCOT has a lot of series capacitors. These are depicted on the map with green and red circles, and they're there to improve power transfer. But what we found is a lot of them are located in high renewable potential areas. So we are seeing a huge number of renewable inverter-based resource connections connecting very close to these series capacitors. And in fact, I zoomed in here near the Cenizo and Del Sol station. We have a lot of renewable resources connected on this multi-segmented line. And this is very common. A lot of the other series capacitors are seeing this as well. And this presents a very challenging modeling and study scenario. The series capacitors make the area electrically difficult to interconnect to, and having so many different types of models in the same simulation does become a bit challenging. So I'll talk briefly about some of those challenges. One is the transient voltage discharge from the series caps. Another, of course, is subsynchronous resonance or subsynchronous oscillations. And I already mentioned the one about confidentiality when you have multiple manufacturers involved. I'll talk a little bit about transient overvoltage because this one isn't talked about as much near series caps. But basically, when you have a series capacitor and you run a simulation where you fault one end of the line segment, the series capacitor will actually charge up during that time because it's effectively connected line to ground in shunt. And then when the fault clears, this accumulated energy will discharge back into the system and in the form of a voltage transient, as you can see in the figure here. And we have seen voltage transients as high as 2 per unit instantaneous. And as you might guess, this creates a potential problem. Mainly, it's a short transient, so it doesn't really affect transmission hardware, but we've seen that a couple of renewable plants are tripping for it in simulation. And this is not surprising because when you have very high voltage peaks, it's really exceeding the hardware withstand capability, and so the renewable projects are tripping to protect themselves. Right now, it's not considered a reliability concern because there's only a couple projects actually appearing to trip in simulation, even though we have a lot of generators near the series caps. And they typically only trip under low output. So under higher output, there's enough losses that the transient gets absorbed or the generator is not as sensitive to it. But it's something we're watching in case it becomes a greater issue, and we will investigate further. Subsynchronous resonance. This has already been well discussed in the past. I will just mention that experience has improved greatly among manufacturers. Their controls are much more mature, but still challenges remain connecting very close to series caps. Some of the challenges, of course, are the confidentiality issues and the fact that SSR studies require many scenarios, so they're very computationally intensive. And the reason is because these are pretty much one-time studies. You can't run them online in operation. So when you do an SSR study, you have to envision all these future scenarios. And so our typical sensitivities include contingencies, dispatch scenarios, and leading, lagging power factor, etc. And we have seen these make a significant difference in the study results. So these studies can have a lot of scenarios, and it makes it difficult for manufacturers to tune their controls to pass all the scenarios. Wrapping up, some final remarks. We do see a lot of complications modeling inverter-based resources. It's not so much because they have black box models, but it is because they're complicated devices themselves. And we have a lot of studies and a lot of interconnections going on. We typically review 20 to 30 SSR studies every year for new interconnection projects. So it is a lot to keep track of. Ensuring model quality is a constant battle. There's a lot of small things that could become issues if overlooked, and that's why we've developed kind of a several faceted model quality requirement program. And so it just requires constant vigilance to make sure we have good high quality models for our studies. Here are some references. Top parts, you can learn more about our model quality requirements. The two bottom ones are tools that can be used to run our model quality requirement simulations, testing out the PSSE model to use the DMView tool, or testing out a PSCAD model, we use the PCAR tool. So you can check that out if you're interested. I hope you enjoyed this presentation. If you have any questions, you can email me at the email address on the first slide. Thank you.